Okay guys, and welcome back to question 2 of the British Algorithmic Olympiad 2022 paper round 1. I've already made a video solution for question 1. If you haven't seen that, make sure to check it out on the studywave YouTube channel. And if you already have, then I've also got links in the description to the GitHub repo for all of the codes to this paper that I've written myself. There's also a Discord community link and a link to our website. Okay. Let's jump into question 2. Sonar. A new fleet of British naval ships have been built and will soon be deployed in the Atlantic Ocean. These new ships have been designed specifically to protect their crews at night when the ship is stationary. Each is fitted with a certain number of depth charges which detonate when they detect a nearby submarine or ship. These ships all have sonar systems. All of these ships have a sonar system which is highly effective. The only problem is that the crews lack the knowledge of how many depth charges to deploy each night to maximize resources and protection. Each ship has a protection level P, which determines the safety that the ship requires each night. Ships with a higher level will have more charges on board. An intelligence team in London has determined the most effective way of deploying charges using the Nautical Grid Positioning System, NGPS. This system relies on the idea that the area of ocean that surrounds a ship can be modified as a grid of squares of water. Each ship has its own respective P by P grid. The top left of the grid has coordinate 0p. And then over here we have some examples. Okay, first let's read the bullet points. So the team concluded that each crew should keep to the following instructions. So instruction 1, use the sonar to emit a signal from the ship which is located at a certain coordinate within the NGPS. Okay, so there's a certain coordinate in the grid, which is the ship, and it's emitting some kind of signal, okay? And then place a depth charge C where the signal crosses a vertex of the NGPS grid. Okay, and do not place any more charges directly behind C. Okay, so let's read the example. So for example, when a ship with P equals 4 and coordinates 2, 2 sends out a signal, so I'm guessing this is this one. When it sends out a signal, it first hits 4 inner vertices, then another 4 vertices. Following it hits 8 new vertices as shown. The total number of required depth charges in this example is 16. Okay, so you can see that the ship is located in the middle, and it also says over here that the top left of the grid has coordinate 0p, so this has coordinate 0p. I don't know why they've worded like that. It's much easier to just say that this is the origin. So let's just stick with that. This is the origin. And what else? So we can see that the ship is in the middle, and it emits these circles, and as the circles hit the lattice points on the grid, then we place a depth charge. So you can see that the smallest circle is this one, and then the one after that is the one they've drawn. And then you can see that the one after that is this one. And yeah, and an important point is this one over here. Do not place any more charges directly behind C. So notice that, for example, over here, this one was actually meant to be hit. So these 4 vertices over here were actually meant to be hit before the circle that's actually drawn here, because notice that here the radius is what? It's 1 squared plus 2 squared, which is 5, and then square root 5. Whereas the radius over here is just 2, and square root 5 is slightly bigger than 2. So these were actually meant to be placed, but the reason that they weren't placed is because of this last bullet point. Because it says you cannot place any more charges directly behind C. So another way to translate this is that as the sonar keeps emitting new circles, then it can't hit it can't place any more charges on that circle if there's already a charge on the straight line that connects that point to the ship. So that sounds a bit waffly, but notice that over here, when it hits the point, there's no more charges on this line towards the center. Whereas if we were to try and place a charge here, we can see that there's already a charge here, so we can't place it. So that's basically what that means. So any points on the same line cannot be placed, basically. So then if we look at the next example over here, it says the next example shows a similar situation, but the coordinates of the ship are 1, 1. The total number of charges required is 18. So yeah, instead they've moved it down over here. And yeah, you can see that as it emits, again, there's no points over here because these are on the same gradient as this. So that makes sense. And then again, there's no points here because these are on the same line. Okay, so I think this problem is starting to make a bit more sense. So what is the first question? So part A, for 18 marks, write a program for the ships to use that finds the number of charges required for a ship to deploy on a given night. The first line of input will be the value p, where p is in between 2 and 2 to the 9. And the second will be the coordinates of the ship, where x can be an integer. So this over here, just fancy way of saying x can be an integer, followed by y, which can be an integer. Okay, so that makes sense. So we have a value of p, which basically just tells us how big our grid is. And notice that p is equal to 4 means that there's 4 boxes. So if there's 4 boxes, we actually need 5 vertices. So since we're going to be using everything according to the vertices and not the boxes, so we're actually going to have to increase p by 1 when we're making our grid in our C++ program. Okay, and then here it tells us the actual coordinates of the grid, or of the ship on the grid. And then here we just have to output the final amount of depth charges. Okay, so again, like initially you could go for something like a breadth first search or a depth first search, because essentially all we need to do is basically go through all of the points on the grid, go through every single one, and check if there are any points that are on the same line as that point. And one approach that I did is that we're basically going to do a breadth first search. So if you actually look at the sonar is basically mimicking a breadth first search. It's kind of going in levels. So it's doing everything that is closest. It finishes that level and then it goes on to the next level and so on. So this kind of mimics a breadth first search kind of action. And the only slight tweak that we're going to have to make is that when we're doing the breadth first search, what we're going to do is we're going to say this. Say, for example, the ship is over here. So we have the ship. And the current point that we're investigating is over here. So this is the point. And what we're going to do is we're going to find the change in x between the ship and the point, and the change in y. So this is basically remembering that the gradient of a line is just the change in y all over the change in x. And basically what we're going to do is that every single time we discover a point, we're gonna basically extend this line till we hit the outer like edge of the grid. So we're gonna find dy by dx, and we're basically gonna multiply by 1. So in this situation, like there is 1 dy by dx, so this is in its simplest form. And then we're going to find the next dy by dx, so the next lattice point which has the same gradient. And then we're going to keep doing that for every single lattice point, and we're going to basically mark these points over here as discovered. We're somehow going to mark them as discovered, so that we know that these points definitely cannot be depth charges. But the only thing is that we can't simply skip these points in our traversal, because they might have a point right next to it that needs to be discovered. So basically these points on the same line still need to be traversed, but we can basically mark them, like almost mark them as done, or like mark them as like definitely no charge there through every single point that we traverse. So when we traverse a point, we find the gradient and we extend that gradient to make a line, and then every single point on that line we mark it as no, basically. That's not a depth charge. So yeah, that's the basic strategy. So how are we actually going to do this? So let's come up with some code. So we're going to say that we're going to have like a grid of integers, which is going to be p plus 1 times p plus 1, because remember that if there are p squares, then there's p plus 1 dots, kind of. And 3 is going to symbolize no depth charge. So this is going to mean that there's definitely no depth charge is going to be placed here. And then 2, this is going to be like the ship. So we're not going to actually want to count the ship, because that's going to be our first node in the queue of the breadth first search. And then we're going to have 1, which is going to symbolize that there is a depth charge. And then 0, that's going to be the default value when we make the grid. So this is going to be unknown. We don't know if there's going to be a depth charge here or not. And by the end, at the start, every single node will be a 0. And by the end, every single one will have to be a 3, 2, or a 1. Okay, so that's our basic strategy. So what are we going to do? First, we're going to pass the inputs. Then after we pass the inputs, we're going to create our grid. So this is going to be initialized to zeros. Then we're going to do a breadth first search with the gradient skipping technique that I told you. So with gradient skipping. And we're also going to track the number of depth charges. So every single time we place a depth charge, we're going to track it. So track depth charges. And then the final step, what we're actually meant to do is just output depth charges. Okay, so let's actually go to the code editor and see how this looks like in code. Okay, so I've got the code editor open here. And yeah, okay, so if we just go to part A, the first step is obviously to input P, so like I called the center X and center Y basically where the ship is. So this is the X coordinate of the ship and the Y coordinate of the ship, and we're simply inputting these over here. And then we're making our grid of integers, and we're just initializing every single value to 0. And we also need to keep track of a visited grid, because we don't want to get an infinite loop. So if we've already visited a node, then we don't want to visit it again. And we initialize all of these to false as well. And then over here, I'm simply setting the value of center Y and center X as number 3. So in this case, we don't actually really need to have a separate number for the origin and the depth charge. So this could actually be a 2 as well, and it shouldn't really make a difference. I'm just going to keep it as this for now, just in case there is a difference. If there isn't, then I'll probably change it. And yeah, this is using the same code that we wrote before. And then also, we're going to mark the ship as visited, because that's the first node in our traversal. And then we're making a queue for the breadth first search, and we're pushing the first coordinate, which is just the ship, into the queue. And this is actually going to keep track of all of the depth charges that we're placing. So now we can actually start the BFS algorithm. And this is quite typical of a BFS algorithm. So while the queue is greater than 0. And now we're basically getting the coordinate. So basically I'm making a pair for every single coordinate, which has the X and the Y value. So I'm just extracting these from the pair in the queue. And then I'm checking if the value is a 0. So if it's a 0, it means that we don't know if there should be a depth charge there. So that means that we should place a depth charge there, because if we don't know, then that means it hasn't been disregarded yet, so we should place it. So then we update the grid as a 1 to say that there is a depth charge, and we add that to our counter. And then we get rid of this, this coordinate from our queue. And now this is where we do the gradient skipping technique. So we find the change in y, which is y minus center x, because y is the current point and center x is the ship. We do the same for x. And then we set I is equal to 2. So this is basically going to be the counter that checks which lattice point on the gradient we're currently on. So it will make a bit more sense later, look. So now what we're doing is we're checking, okay, while dy is not equal to 0 or dx is not equal to 0. So this is basically an edge case where on the very first node, there's going to be no change in y and x because it's like the ship is equal to the point. So we're just going to be stuck in an infinite loop because a point is not a line. So there's no points that we can actually skip basically. So that's what that does. And then over here, I have a valid coordinate function. And this basically just checks if we're actually inside the grid still, because remember that straight lines are infinitely long, but the grid is finite in size. So if we go up here to the validate coordinate, all this does is just it gets the coordinate of P and checks if it's still in bounds. So that's all that this does. And then over here, we're checking if a point has already been disregarded. Because if a whole line has already been disregarded, then we don't need to disregard it again. So if we have even one point on that line that has been disregarded, then that means the whole line is already done. So there's no point in iterating to the next line. But this is like very minor. This doesn't really affect the runtime. It's just a minor optimization, this. So then actually inside the while loop, we're just setting every single point. So we have the change in y and we're multiplying by I. So basically we have a change in y, which is the distance from the ship to the current point. And we're basically going along the lattice points of this line and then marking them as no depth charge. And then we're increasing I so that we keep going along this line. That's basically what it's doing. And also remember that we don't mark it as visited. We only just make sure that there's definitely no depth charge here because we might have to visit nodes around this node as well. So yeah. And now all we're doing is we're just adding all of the adjacent points on the grid. So if we have a point, then we're going to add the one that is directly above, to the right, below, and to the left of the current point to the queue, because we want to basically traverse everything. And once we add them to the queue, now we actually want to mark them as visited, because now they're actually being investigated. And yeah, that's all that it's doing. And now if I go to the mark scheme over here, and I go to question 2, and I just get the final test case, because this is meant to be the hardest one, you can see that if I compile this, so 2.cpp and a.out, we can see that it's blazing fast. So it does the last case very, very fast, and the answer is correct. We can double check. 611584, 611584. So the solution works, and that's all good. Okay, I guess that's everything for part A. Let's move on to part B. Okay, part B for 2 marks. A ship S has coordinates 0, 0. The point Q has coordinates 98754, and 123456789. Assuming the value of P is large enough, determine whether a depth charge would be placed at Q. Explain your answer. So as we saw before with our gradient skipping technique, remember that every single time we encountered a new point which hasn't been marked as no depth charge, then we found dx by dy, and then we kind of extended that line to all of the lattice points on that line, and then we marked these as no depth charge. So notice that the first point on this line is going to be the one that is closest to the ship. So this is the ship. And when is that point going to happen? And that point is going to be when dy by dx, like the actual fraction itself, cannot be simplified anymore. So in other words, dy and dx are co-prime and their greatest common divisor is 1. Because over here, basically what we're doing is this point over here is going to have a gradient. If we actually were to compute the gradient, then it would be 2 times dy all over 2 times dx. So that's basically why that wouldn't work. So we need to find the point that is going to have basically the most simplified gradient. So what we have to do now is we're going to say, okay, so this is the y coordinate and this is the x coordinate, because remember the ship starts at 0, 0, so we don't have to do any offsetting here. And all we have to do is find y over x and check if it can be simplified. And if it can be simplified, that means that this point is somewhere already along this line over here, for example, and a point has already been placed over here. So that means this point cannot actually exist. So if we actually go into C++ now, I've got the code editor open now, we go to part B, all I've done is I've found the greatest common divisor of these two numbers, and then I've just divided them by their greatest common divisor to output the first coordinate on that line which would be placed. And if this outputs these two same numbers, then these would actually this would actually be on the grid. So there would be a depth charge placed at Q. But if these numbers are different when they output, that means that they have been simplified and a depth charge has been placed closer to the ship on the same line. So if I actually run this now, I need to actually activate part B. So 2.cpp and a.out. So then we can see that the output actually outputs numbers that are not equal to this, to these two first numbers. So that means that the point Q is not going to be on the grid because there's already a point closer to the ship on the same line. Okay, and that's everything for part B. Okay, question C for 5 marks. A new ship H, where P is equal to 999, is located at 1, 1. Suppose you were to draw straight line segments from the ship to each deployed depth charge. A nautical triangle is a triangle formed by the grid boundaries and the line segments. For example, the nautical triangles in this 3x3 grid have been highlighted. Determine the number of nautical triangles for the ship H. So just as a few examples, this is one triangle. Actually, I'm probably gonna get the highlighter. So this is one triangle. This is another triangle. This is another triangle. So you can see that these are all of the triangles. So a triangle is basically a point that's taken from the center and connects to the edge. But the only annoying thing is that there's actually an extra triangle which you need to consider, which is this triangle over here. And this is because the question actually says that we need to draw straight line segments from the ship to each deployed depth charge, and the actual triangle is formed by the grid boundaries and these line segments. So they don't actually have to be strictly only connecting from the center. They just have to be from line segments and connecting to the edge of the grid. And you can see that generally, since the point is at 1, 1, this is going to be the only triangle that actually looks like this. And I'm not really going to go into a proof of why this is true, or I wouldn't even be entirely sure how to prove that. But it's just generally quite easy to see that this is going to be the only triangle like this. But if you didn't spot this one-off case, you actually only lost 1 mark. So if I actually go to the mark scheme, and yes, definitely check out the mark scheme, you can see that they actually still give you 4 marks if you didn't spot that one-off case. But if you did, then you get the full 5 marks. So yeah, that's that. And now we have to ask ourselves, what actually makes a triangle? So if we look at all of the cases that connect from the ship to the outer edges, notice that if there are 2 edges, if there are 2 charges on an edge, then that's going to make a triangle, right? So for example, these 2 make a triangle like this. Then similarly, these 2 also make a triangle. They make a bigger triangle. So now we just have to ask ourselves, how many of these points are there on the edges? And once we find how many points there are, we just have to choose 2 of them. So here we know that there are 4 points. So how many triangles are there? Well, out of these 4 points, we need to choose 2 of them to be part of the base of the triangle. So in this case, there would be 4 choose 2 for this edge. And then for this edge, how many are there? There's 1, 2, 3, 4. So then again, there's 4 choose 2. And then for this edge, how many are there? There's 1, 2. So now it's just 2 choose 2, which is just 1. And then again, for this one, it's 2 choose 2. So we add 2 choose 2 again. So this is how many triangles would be in this one. And then obviously we'd have to add the one-off case. So now we can actually translate that into code. So if I open the code editor and we go to part A again, I didn't actually make another function for C because the first thing to do is that we actually need to place all of the depth charges. So in order to do that, first let's actually uncomment this. So uncomment it. So that activates part C, and we don't want the output from part A. And what are we going to do now? Well, the first thing is that we have to make our own input. So it says that P is equal to 999 and the ship is located at 1, 1. So that's our input. And we're basically going to just use part A to populate the entire grid with depth charges. And then we're going to traverse through the grid counting the boundary charges. So the boundary charges array here just counts how many charges are there on the top edge, the right edge, the bottom edge, and the left edge of the entire grid. And then we're just going to loop through from 0 to P. So we don't actually need to loop through the whole grid. We only need to loop through the edges. So we're looping through the edges and we're checking if it's equal to 1. Because remember, if it's 1, then there's a depth charge. And this is checking the top edge, the right edge, the bottom edge, and so on. And if there is a depth charge, then we increment the specific location or the edge that this depth charge is on in the boundary charges array. So in this case, there is, if this condition is true over here, then that means that there is a depth charge on the top edge. So then we increment the amount of depth charges in the top edge in the boundary charges array. Remembering that index 0 tracks how many charges there is in the top edge. It's a bit confusing, so many words, but just take a second to try and read and understand it. So then once we do all of this, then we're going to have all of the charges on each edge nicely in an array. And then all we have to do is just go through each, well, now we're going to initialize a new variable to check how many triangles there are. And then we're going to go through each edge in the boundary charges array. And we're just going to do choose 2 with how many charges there are on each edge. And we're going to add this. And in C++, obviously, there's no inbuilt NCR function, so there's no choose function. So the way that I've done it is I've made my own NCR function. And since these charges are probably going to be quite big, I didn't use the default factorial way of doing it. So instead, I used the recursive approach, which makes use of Pascal's identity. So if you actually Google this up, you'll definitely find explanations of this. This is basically a nice way to compute NCR without getting any overflows. And yeah, so that's how you answer question C. And now if we actually run this, So compile and then output. Oh yeah, we need to use part A here. Compile, run. So you see that took a bit of time to run, but this is not a program question, so we don't need to worry about it being over 1 second. And then we can see that the final output is 1247,503, which is equal to the mark scheme. So if I go to the mark scheme here and we scroll down, yeah, we can see that this is the answer. I remember that we had to +1 for the edge case. That I probably bet that a lot of people missed out on this, but that's not even that bad, to be honest. Okay, so that's everything for question 2 in the British Algorithmic Olympiad 2022 paper round 1. Again, all of the code is in the GitHub repo in the description. Definitely join the Discord community if you want to link with other people who are also trying to prepare for this test. And yeah, I'll see you in question 3.